welcome back to Computer Networks, week 16. Well, this is in fact the last lecture. Yeah, so the announcement was already given last week. Number one is quiz 41 and 42 we'll be doing this week. And then on Thursday, we'll have the last exam, and that's all for the semester. Okay, how do you like that? And today we'll start from quizzes. Okay, so these two quizzes are about bad news traveling slow on distance vector. So this is related in case that there is some changes on the link cost over the entire network. How do we make sure that distance vector will converge, okay, to the true routes? It's a little bit tricky when the link cost change is going the bad way. Okay, so let's take a look at the first quiz today. Quiz number 41. Let me go to the quiz. There. So this quiz is bad news travel. So, oopsie, let me go back. So you see that the change, okay, here, going from cos 4 over link xy is suddenly really bad to 60. Okay, so now let's calculate x and y's table right after the change. So no worries, let me try to set you up for the quiz. So this is the topology, the network, and we're changing the link cost between xy to 60. And these are the tables before the change. That is saying that in no x here, dx is 0.45, okay? And dy and dz here are provided by no y and no z. Similarly, dy maintains and calculates its own dy. Okay. In the meantime, y here tracks the distance vector from x, okay, which is essentially dx here, and this is essentially dy, dz from z, right? After the change, well, x and y will both need to recalculate the dy for y and dx for x. So here, what I'm asking is, what will be the new dx after x recomputes? Okay, and what will be the dy after y recomputes based on the Bellman-4 equation? And just to make sure that you do not miss the point of doing Bellman-4 recomputation or computation in general, let's focus on no x and calculating dx. So in dx, we do have three entries, right? dx, x, and what? dx, y. And what? dx, z. Now dxs is always trivial, which is 0. Therefore, what I'm asking you to do to recalculate dx is essentially recalculating these two entries. So this is question mark number 1, and this is question mark number 2. So let me remind you how the Bellman-4 equation should look like to calculate dxy. So this is calculating the shortest distance from x to y. So you see that we will need to try, right? Asking the two neighbors of x. So this is going from x to y, and asking the two neighbors, neighbor number 1, y, and neighbor number 2, z. So x is right here. There are two possible neighbors, one here to exploit to go to a particular destination. So you see here, neighbor, neighbor. Okay, now calculate what is the value here for dxy, for dxz. So we could update dx right after the route change. Okay, work on it. So I'm gonna also need the route change for dy's table. So give me dx as well as dy. Oh wait, is 50 on? No, Jiahong, 50 is actually 50. Let me check. Okay, let me just go back a side to make sure. Yeah, so in the original quiz 40, yeah, so this is actually set to 50. In the previous quizzes, it was 7, I know, because as I flip back here, right? So in the previous quizzes, it's actually quite simple, 217. But for quiz 41, we do have 4150. 4150 to begin with. Okay, and let me come back here. Yeah, so dx first and dy. Okay, so this one is going to take a little bit of time because you need to follow the Bellman-4 equation there. As human beings, it's very straightforward, but if you are a router running distance vector, things can be rather unintuitive. Yeah. Oh, I see what you guys are saying. I see. Okay, this is good. Good, got it. Emily, Jia Hong, I see where you're confused. Let me try to make the changes on the fly and see if I can do this. If xz is 50, then this is still 5. Yeah. Yeah, so original dzx will still be 5 because, you know what, the reason that the original table look like this is because this is an entry that's after going through several iterations. And dz here has already figured out the shortest path to x, okay, is actually going through y and then x. That's cos only 5, which is shorter than going directly z to x, which is 50. Okay, so what I did not say is this. Okay, the original tables there are actually the result of going several iterations, and the network has already converged to the shortest path. Does that make sense more now? Jia Hong, Emily, let me know. All right, very good. Yeah, so you see, if the column on the left is to initialize, yeah, it's definitely wrong. Very good, guys. But the column on the left there is actually to describe the routing table after the original graph converged to the shortest path. Okay, so the column on the left is not the initialization table. Very good. So you guys recall how we do distance vector routing, right? If xyz with 4150, we just need to start calculating, deriving the distance vectors. Then yes, you guys are right. Okay, dzx should be initialized to 50, dzy initialized to 1. Yes, we answered. Yes, exactly, Jingyuan. We answer right after the change. What is the first iteration? So I call it T0. But it's okay. This is the first iteration of computation. Okay, although we have not yet really propagated distance vectors to the neighbors yet. Because if there needs to be a change here, if dxy and if dxy and dxz here need to be changed, yeah, so this vector will need to be propagated to the neighbors. Okay, so this will then be the first iteration of new dv propagation. Exactly. Okay, I think you guys have pretty much get the idea. So we just need to find out what is the new dx and what is the new, sorry, let me use a pen here so that it doesn't look too ugly. What is the new dx and what is the new dy? New dx, and here we will have also a new dy. For new dy, we need to recalculate dyx and dyz. And by the way, this is something that will definitely appear in the exam, so let's make sure that you get this right. Oh wait, someone has already answered it. Cool. Interesting. Okay, so team A here, James on behalf of team A says dx should be 0, 65, 50 and y should be 60, 0, 1. Oh, okay. The final answer should be 0, 50, 1, 50 and 51, 0, 1. I see. Yeah, because right after the link cost change, you thought that you changed the cos xy to 60, y to 60, because the link cost obviously changed from 4 to 60. But James, you are still thinking a little bit like human beings. Okay, the way router X works is strictly doing the change based on the Bellman-Ford equation. So in a way, James, you are thinking a little bit more. What router does is simply get this and simply get this. Okay. Let's see. Samuel also come to 51 and 50. And here is 51 and 1 for dy. Very good, you guys. Guangzhao think a little bit differently. 60, 50, 61. Interesting. Because this is simply changing xy, right? Based on the new link cost. But Guangzhao, think again. Router X there does the recalculation. So this value, how does the calculation work to get this value? Think a little bit more. Let's see. Oh, Jiahong, you've got it. Jiahong is, very good. You should consider being an actor. Exactly. You need to pretend that you are router X, and router X recomputes dxy exactly following a equation. Okay. And between 60 and 51, take the minimum, 51. For this guy, between 61 and 50. Oh, 50. Similarly, for dy, big dy, this entry 60, 0, 1, 50, therefore 51. 1, 0, therefore 1. Very good. Shu Wei here. Ah, okay. Yeah, so you skip the details. Here you get also. Oh, okay, you already get a thumbs up. Okay, let me just add to that. Hong Shen here. Very good. Ziya. Great. So this is for no table. Perfect. Very well done. Okay. I like that you managed to line things up like this on Slack. Nicely done. Xi Ai. There you go. Nicely done. Kevin. Kevin got 60 and 6. But check again about ZX. I think this is still. Is this still 5? Or YZ? Yeah, YZ is 50, right? ZX was 5 or 1, I forgot. XYZ. Yeah, I think something might be a little bit mistaken here for this entry. Yeah, so Kevin, you can actually work on it a little bit later. Let me go back, maybe. Okay, so this is Ziya's table. Let's see. 60, 0, and then cost between cost between x2 y to y, y to z, and then z to x. So maybe Kevin is right. Interesting. Is it 50 or 6? Is it 51 or 6? Or 50 or 6? Okay, so this is a little bit mysterious, right? dyx. Let's see. dyx. Yx to x. Yz. Yz is indeed 1, right? But Zx is 50. It is not 50. So I think Jiahong, yeah, I'm also mistaken myself. Kevin might be the one. All right. Being correct. Wonderful. Okay, it's 100 point plus a medal. Kevin here. Very well done. I think the problem, right here. Didn't we calculate in order like I see? You are right. You are right. Wei Yao here. 50, 50, 51, 1. 51, 50. Okay, so I think after going through several of you, 51, 50 for distance for dx, this seems to be alright, okay? But for for dx, this is correct. For dy, seems to be a little bit tricky, isn't it? Yeah, so we have another answer being like this. You can see why distance vector, a question like this, asking you to derive the table is definitely going to show up in the exam because it can be confusing sometimes. I think Eating have got it. Okay, edited. So probably originally, right? Team 9 also thought about that should be 51. Yeah. Guys, there we go. Team 2 also discover it's probably 6. I know you guys must be thinking, how can it be 6? There's no way. If you look at the network there, if you look at the graph, obviously, right? As human beings, 6 is not possible being the shortest path cause. Okay, Yuzhe also got it. Good, I guess you guys also see what's going on there. And some of you might pick up, Ziya also pick it up. Very good. It is indeed tricky, guys. Alright, so let's walk through. I have prepared the video and let's walk through how poly derives dx and dy. So the video is only
quiz
like
35, the scenario is a bit tricky. Let's try to be patient and walk through the derivation of dx for no x and dy for no y. Let's start from dx. Let me just show the final result real quick. The xy here, the first value should be 51. The xz, the second value here, should be 50. Okay, and the detail is this, again, from the source to the destination. So the xy, the source is x, destination is y. Through two neighbors of x of the source, that would be y and z. So we have y and z here. So link xy costs 60. Link xz costs 50. So we do have 60 and 50 here correspondingly. And then through first neighbor y, what is the perspective? What is the shortest distance to the destination? Well, y to y, we'll have to look up the table coming from no y in order to find out, right? That is y's perspective. So that's in dy coming, came from no y earlier. So dy y, then it's 0. And then, for the second neighbor, z, what is z's perspective, the shortest distance to y? That will be what? dz to y. So dz to y. And that is in, distance vector of z came from no z earlier. Z to y, it says 1. So we put 1 here. So sum of trying through neighbor x, 60. Sum of trying through neighbor z, 51. Therefore, no z here wins, and the shortest distance is 51. Similarly, we derive dxz from x to z. So clear the markup from x to destination z. There are two neighbors again, y and z. X to the first neighbor y costs 60. X to the second neighbor z, link costs 50. So again, 60 here, 50 here. And then from y, what is the shortest distance to z? Shortest distance from y to z, that would be y to z being 1. And then the second neighbor, z's perspective to go from z to z. Shortest distance from z to z, z to z, 0 here. 61 compared to 50, so we pick 50 as the shortest distance from x to z. Now, it's not so bad. Okay, let's derive next. dy. Okay, again, let me put up the solution first. So dyx, the first entry here, you thought, right? It should be 60, obviously, but this is, hey, as a human, you see the global topology, you know it's 60. But distance vector is actually what? Making decision based on local information, based on information provided by the neighbors. So let's be careful and then still walk through the Bellman-4 equation. Okay, so dyx, source being y, destination being x. Going through two neighbors, x and z. Link cos is link cos yx is 60, link cos yz is 1. So we have 60 here and 1 here. Now, going through neighbor x, what is the shortest distance to x? dxx, we'll have to look up the table, dxx, which is 0. Going through neighbor z here, what is the shortest distance from z to x? Z to x. That will be looking up the dz vector, okay, and going to x. So it's this guy here, 5. So we put 5 here. And you know what? Bellman-4 equation says comparing 60 to 6 wings. Okay, and that is actually going through no z. So y is going to pick. Okay, saying to go to x, let me send it to z first, and then z says, I know a way to x, which is, yeah, the old impression, right? This way. So you see the packet there is going to go y to z, z to y, but y is going to say that, hey, to go to x, you need to borrow z, okay, as the middle point. So that packet is going to loop around between y and z for a while. Interesting, isn't it? Yeah, this is actually a very interesting characteristic of distance vector. Okay, before the route actually converges, the packets could potentially be in a routing loop. So 6 here, again, is the new dyx. Okay, it's not quite yet the true, okay, dyx. Okay, so you see here, even though y is capable of detecting, there's a link cost change right here. Okay, but y's routing decision, route calculation, is still based on the ODX and ODZ. Okay, and right at the link cost change, no y, okay, have not yet received the new DZ, new DX yet. So y is going to be using the ODZ and ODX. Therefore, you see, okay, the ODZ is telling y the shortest distance from z to x is 5 here. So we will be, in the short term, okay, under the false impression that this is the best route. Y sent to z, okay, and z will somehow know a way. The cost is only 5 to x.
Yeah. Okay. Tricky, isn't it? But I guess you see a little bit better. Because you need to, use information from your neighbors. But before the neighbor can send their update, because they are still doing the computation, just like y is doing the computation while x is redoing the computation, right? So y there will not be able to receive the updated information yet, and so it's making decision based on local information now. Okay. Now let's try to continue the bad news goes slow example here. You see here, topology the same. We just finished calculating x and y's distance vector right after detecting the link cost change. Now the thing is that after the recomputation, right, there's some new information. X and y will need to what? Propagate the new distance vector to the neighbors. Okay, so we have not yet converged. We just do the computation right after the link cost change. Now, the next part of the problem, the example here is to ask you to calculate z's table, okay, after the first iteration. And then Q2, y's table after the second iteration. which is this. We just finished calculating x and y. Zx and zy. I'm sorry, dx and dy. Okay, so the next iteration. So this is going to be propagated to both neighbors. This is going to be propagated to both neighbors. So z essentially will receive dx and dy coming from no x and no y. And triggered by this, z would recalculate based on the Bellman 4. Okay, can you tell me what dz is at t1? Okay. And can you tell me, because once this is computed, z is going to send dz to y and to x. Okay. How would y recompute the new dy after receiving the dz? So I'm asking you to do dz at iteration t1 and dy at iteration t2. Oh, okay. Very good. You guys are very good. So once you get the trick, yeah, I think you should be able to handle these. Let's see. Samuel says, 710 and A01. Let's see. 71 A1 exactly. Shu Wei finds the same, right? Jia Hong. Z being 510, Y being 601. Okay. Let's see. Yeah, I think Jia Hong, you've got it, but because I can tell from 6 here. Okay, so I guess you are the kind of students make really, right, minor errors due to negligence a lot. Let's see. 71, A1, very good. Nicely done. Eating, you got it as well. Angela, very good, very good. Exactly. Exactly. Let me give you, yeah, a pop. Congrats. Very good. I think most of you've got it. Okay, so here's how Polly prepared as a video to walk you through getting the dz at t1 and then getting the dy at t2.
You should get a sense that it's going to take a while for these routes to converge to the shortest path. As to how long, yeah, let's try to walk through the scenario for a couple more iterations to see. So we'll develop the table, okay, for T1 and T2. And at T1, Z here can try to calculate dz because it now received the distance vector of dx and dy coming from no x and no y correspondingly. And so dz here contains two entries, dzx and dzy. Now let's ignore the calculation of dzy as this one is very trivial and we know how to do Bellman-Ford equation already. Okay. Let's go over, however, dzx carefully because this entry here is very interesting. So once again, okay, from source z to destination x, two possible neighbors of z, x and y. So first neighbor here, the link costs 50. Second neighbor here, link costs 1. So we have 50 and 1. And then the final destination is x, so we need to know the value of dxx. Final destination is x, so we need to know dyx. So for these two entries, we do table lookup because this is actually x's perspective. Okay, so this is what x has informed z. So what x has informed z is the dx. So in x vector, okay, to destination x, entry will be 0. In y vector, for destination x, entry value 6. So 50 compared to 7, 7 weeks. And therefore, we update dz to 7, 1. Now, what's interesting is this. Z thought, okay, the shortest path to x is now what? 7. And the best neighbor is z. So z thought, okay, next hop to forward the packet, destination being x, should be y. But you see, y here thought, okay, the shortest distance to x is 6, and the next hop is z, yeah, because z knows a way, okay, much earlier saying, oh, the shortest path to x is 5, and next hop is z. Okay, so you see we have actually looped it 1.5 times, okay, on link y and z trying to develop, okay, what is the true shortest path. If we continue on, okay, as z here finished calculating dz, this is going to go out and reach no y and no x. As a result, no y here can calculate dy again, provided the new dz. Okay. Let me bring up the result. dyx, this value here, is going to be 8. Let's look through it again. Okay, from y to x, y to destination x. Through neighbor x, neighbor z. Link costs 60, link costs 1. Link costs 60, link costs 1. dxx, 0. dzx, look up the table. z's x, 7. 7 here. So, wow, we get A. What does that mean? Yeah, although we update the table for y so that it's 8, 0, 1. But you see, y here actually believe firmly z is the best neighbor to forward the packet because z knows a way which takes only $7 to go to x. And this is going to go on. in fact, because y here is going to announce dy also, okay, to all the neighbors. And z is going to recalculate the dz. And guess what? The next is going to be 9, 1, 0. And back to y, 10, 0, 1. Okay, all the way until when? Until z finally discovered that 50 is the true cost to x. So until, okay, in dz, the value becomes 50, 1, 0. Okay. And how many iterations would that be? Came all the way from 7 to 50, that will be 43 iteration. Okay. And including the initial iteration, that will be what? 44 iteration. Okay. Until z discovered the true path. Next, then y will discover the true path. And then everyone converge to the shortest paths that are really true.
The problem here is, okay, right after the link cost change, when y is trying to recompute, okay, the best route to x to z, okay, particularly to x. Bellman-Ford algorithm says y needs to try, right, calculating the total cost through neighbor x, neighbor z. Through neighbor x, best distance from x to x is 0, trivial, but the link cost is suddenly 60, okay, just to get from y to x. So together, total cost 60. Okay, not very good. But the other neighbor here, z, was still under the perception that the best route is this and the cost is 5. And y here says the link cost between y to z is only 1. Okay, so y is going to insist, why don't I send packet here? Z is going to send the packet on behalf of me and taking only cost of 5 to reach x. Y does not know. Z is actually under the perception that this is the best route to go to x. So z is going to send the packet back to y, and y is going to send it back to z. Z is going to send it back to y. So this packet here is going to loop for a while, okay, until y discover, okay, the real shortest path to x. So z here, okay, being still under the impression that the best route is the one before the link change, okay, needs to know about the link change. Poison reverse is working this way. This is to help, okay, preventing bad news travel slow. In poison reverse, y and x, okay, the two ends of a bad link, is going to tell their neighbors that, oh, all your routes, okay, all your shortest path routes to the other node along the link needs to be changed to infinite, okay. That way, it prevents, okay, y selecting z, okay, as the shortest distance to x. All right, so that takes us to the second topic. And by the way, today the most important thing that I need you guys to pick up is distance vector. Indeed has this good news, travel really fast, but bad news can travel slow, you see. So dzx is going to be 7 in T1, dyx is going to be 8 in T2, right? And what will be next? Right, and no z, right? It's going to be 7, 8, 9, 10, 11, until 44 iterations until we get to, I think, above 50 to 51. Then finally we'll converge to the correct route. Okay. So that was bad news travel slow. Now in case the link cost that we changed is not quite from 4 to 60, but to what? To link 4 being completely broken, then we need to count to infinity. Okay, so this issue there, you see, is also called count to infinity, because if the link cost for that link there that was broken, sorry, the link between x, y here is not just changing the cost to 60, but entirely removed. Such a iteration here, oscillation here, no, not quite oscillation, I don't know. I mean, we keep counting because of having no global information. Is gonna go until infinity, I think. Or is this still 44? Okay, so I'm not quite sure anymore, but oh, okay, I think I know why. No. Okay, then probably think a little bit to let you know why it's count to infinity. Will the change in z also occur? The recomputation of x table. Yes. So although I actually try to go like real quick and ask you only to calculate this and this, is so that I can illustrate quickly, right? We count from 6 to 7 to 8. The next iteration, because the situation only happening between these two nodes. Because z still think, the minimum cost is 5. But the next round is thinking the minimum cost is 7. So y will still be taking this way, right? And then decided that it's 8. But next round, it's going to tell z that the cost is 8. Then z will think that the shortest path to x is 9. You see? So I want to show that there's this, gradually incrementing the cost until finally it's greater than 50 or maybe greater than 60. So now I can recall exactly. So this is a little bit tricky. But I want to showcase this. But you guys are right. I think Kevin, Zhuang Li Kai asked the same thing as Wei Yao is asking. Yeah. In fact, what should be done entirely is this. In iteration T1, x is going to tell z, of course, 0, 51, 50. X is definitely going to tell y also 0, 51, and 50. Now, z at t0 has no change, so this is going to remain the same. So z will not be sending anything out. So this we know for sure. So at t1, this is going to be changed, and the z at node y will remain the same. So node y here needs to recalculate this value and this value as well. So you guys are correct. Okay. So why don't you calculate what this is and let me know. Okay, I think it's still 5 plus 1. Therefore, this remains 6. Okay. So do the calculation. Similarly, right? 601 is changed. We can see, oh, sorry. Very good. Glad that you let me know. Okay, let me do this again because this is important. I know. You guys are probably very confused right now. Jingyuan is saying the same thing. Good. Very good that you guys let me know. Yeah, so let me come back to the slide mode. Okay, so in the quiz, I ask you to calculate dz and dy. This is because if you observe, dzx here is changed from 5 to 7. Okay, because yx is changed to 6. Okay, and this is going to influence y's routing table here. You see this guy gets incremented to 8. And this, in fact, is going to affect z's table again. So the entry there, dzx, is going to be 9. Why? Because at this point, the best way to x from y is 8. So it's thinking, oh, there's a certain way existing from y to x being 8. And z picks that up. 1 plus 8, that's 9. That's way better than 50. The other way. And so z is going to say, hey, okay, I know a way, which is 9 to x. This, again, come back to influence y's decision. Okay, so this is going to grow to 10, 11, all the way until the sum is, until when z sees that the cost going this way is 51, then z will then say, okay, fine. The best way is this way, going directly to x. Okay, now it's clear. Okay, and I hope it's clear for you as well. After 44 iterations, T44, finally, the zx, okay, going through neighbor y is 51, but going through neighbor x is only 50. Therefore, z finally, okay, admit that x directly is the shortest path. Now, in this example, because I need to show you, bad news travels slow. So this is a bad news, going from link cost 4 to 60, really bad news. Okay, and it's gonna take a while to converge. Okay, therefore I did not ask you to calculate the new tables for x and y. But you guys are right. I think Wei Yao and Li Kai are questioning the same thing. Okay, so here, because this is changed in T0, dx here is changed. Therefore, dx will be sent to all the neighbors, including y and z. So we calculated z based on that. But what about this guy here? Dy needs to be recalculated as well, with dx being 0, 51, and 50. Dz will still be 510 because, okay, I should use the pen. Okay, dz will still be 510 because nothing has changed here. So no z here will not be sending anything out. So this needs to be recalculated. Dy here at time 1 needs to be recalculated. Just like dx at time 1 needs to be recalculated because dy is changed to 601 and z is not changed. dz is not changed. Okay, so guys, use the break to calculate dx in T1 and dy in T1 and let me know. Alright. So if this is changed, definitely needs to inform the neighbors. If this is changed, definitely needs to inform the neighbors. Okay, let me come back to another question. This is from James. Okay, let's see. Excuse me, I still don't understand why does z tell y its distance to x is infinite. Okay, so you were talking about, yeah, there are no changes, exactly. So that's why I skipped showing. Okay, let me go back. Yeah, so you guys might find that, hey, dx did not change and dy did not change. Therefore, I did not bother asking you guys to derive these. Yeah. Okay, Shu Wei also find the same. Okay, but you see, did you notice that? Hey, here, I did update dx. Very good, Jingyuan. Yeah, I did upgrade. I did update the dx entry for router wise table. Because I know, I think I did the calculation before and making sure that there's no change here. Okay, so there's only gonna be change triggered at node y and change trigger at no x. So you guys can also try to calculate dx here, assuming the y entry is now 601 and z entry is the new entry, right? So I think it's 810. I don't think dx is changed either. Okay, so these guys, no change. The only tables that are changed are these two. And you see continuously 7, it's counting and counting and counting to a point that finally, okay, this route here, that continue to under the previous, based on previous memory, okay, finally count to a value that's larger than this. Okay, so the reason, I think now I can explain, James. Consider a network that there's no link between x and z. Guys, consider a network that has only 3 nodes and only 2 links, one between x, y, and one between y and z. What do you think? Exactly, right? It will count to infinity because this link cost here is infinite. Alright, so yeah, so it's taking some of our break time, but I guess it's okay. Let's still take a break though, so that you guys can consume this a little bit. And I'm pretty sure that some of you still have questions you want to ask. Feel free. Okay, but we need to get distance vector clear. So let's come back in 10 minutes at 2:28. Okay, so break for now. let's come back. Yeah, I know it's not that straightforward because human beings are just not used to thinking like computers. Okay. Okay, so Wei Yao is asking, I couldn't figure out why there's no change, okay, in T1, the dx. Here the question is, won't the x row in table x at T1 being 0, 6, 5? Okay, according to the change from y. Give me a second. Just go get water. Okay, so this is actually how we derive x row at T0. Okay. I understand the numbers are all wrong, so let's not look at these. Okay, now look at these. But this is still correct. Okay, so let's see. At T1, okay, because now we see it should be 601 for row y, and for z, for row z should be 510. Okay. So link cost is actually the same. What's a little bit different are these. Now, y is always 0, like zz, like xx. Okay, now d zy, zy, still 1. Okay, so 60 comparing to 51, still 51. You see, Wei Yao. So dxy, this entry here is not going to be changed to 6. And then for dz, that's calculated. Well, this is fixed. Okay, and this is definitely 0. So these 3 entries, no questions. dyz, 1. So, Wei Yao. Still 5150. Yeah, because hey, you guys are all smart. I think to do distance vector right, you require a machine. Okay, for human beings, it's just, right? I get to see everything. How can it be so weird? Yeah, so this is how the human brain and are different from the computer brains. Yeah, all the computation is based on what the memory says there in a computer. The information, if the information is misupdated, then you get to have that situation. Now another thing, there's a question appearing in, I think, Ask Us Anything. Yeah, and I think this is Samuel when I was saying that this is called a count to infinity problem the first time. I don't have a good example for it. But now later you see that I say, if you consider the topology, the same topology, but without the link between, let me see. So that's assume the same topology except that there's no link here. So there will be just x and, and y and z. And just these 2 links, okay? 4 and 1 to begin with. Okay, and we suddenly change this to 60. So the count there between this row and this row will go on to infinity. Okay, I hope that is clear. Okay, because in this example, you see the count needs to go greater than the link cost here, right, in order to fall back to this path. But here, there's no path. So it's going to go counting forever. Okay, so it won't converge at all. Okay, I hope that is also a little bit more clear. And that is why, okay, we do need Poisson reverse, okay, which is what we just talked about in the previous video. Here is to illustrate how Poisson reverse can help, okay, avoiding count to infinity. So what I'm trying to say here is that we need to count when there's bad news. In certain situation, for example, a network like this, we not just count, we count to infinity, and it will never converge. The packets will just loop forever. So it's not like, it will take some time to converge like this case. Therefore, there needs to really be a serious solution, okay? And that is called, sorry. Yeah, I know, I forgot to show this again, right? So in this case, we count, but we do not count to infinity. But for this case, we'll count and we'll continue to count forever. Okay, so it will not go away after some amount of time. This is seriously bad if this goes on the internet. But you know that this is not very likely. It only happened in a string topology, where from one node to another node there's only one way. Yeah. But still, in case there's a local network, somehow the system admin, network admin configure it this way, then not good. Therefore, we do have this Poisson reverse here, okay, trying to address the issue. Okay, and let Polly illustrate in this video and show how we could Poisson reverse and avoid count to infinity.
Let's use the same example to illustrate how Poisson reverse works. So, taking one step back, before we have the link cost change. Now Z here will discover a shortest path to X this way, Z, Y, X. So shortest distance from Z to X is 5. And the next hop router is Y. Now, link XY here, the cost changes from 4 to 16. X, Y, these two routers being connected to the link will be able to discover the link cost change. But Z here being farther away couldn't. As a result, Z will be telling Y, hey, this is the shortest distance from me to X. And that's why in quiz 35, we're calculating the shortest distance from Y to X. We ended up having this, right? Because Z is a neighbor of Y, link cost is only 1, and Y is being told by Z, 5 is the shortest distance to X, therefore we do 1 plus 5, and we ended up having 6 here, okay? A funny value for the shortest distance from Y to X, which we see from the network after link cost change, there's no way this is the right value. So to avoid, okay, having confusion such as this, we should stop, okay? Z from keep telling Y, this is the shortest distance. So Z tells Y instead, okay, the distance to X is not 5, instead being infinite. That is what you're seeing here. Distance from Z to X at Y's table now being infinite. And how do we achieve that? It's not that hard. So if this is the link having a link cost change, we ask the node right adjacent to the link to try to probe the neighbors. Okay. If this node here discover there's a route coming from the neighbor and using itself as the next hop. Okay. So if Y here discover in one of the neighbor, okay, and this neighbor is using itself, okay, as the next hop to a destination. Okay. Set this entry here in Y's table to infinite. With now the Zx being changed to infinite, the way we calculate the Y in iteration T0 will be different. Okay, so dyx particularly is the entry with different value. It was previously 6, okay? But now let's see how it's going to look like. From y to x, okay, there are two possible neighbors, x and z. Link cost to the first neighbor, link cost to the second neighbor, 60 and 1. And then from first neighbor x to destination x, dxx. From second neighbor z to the destination x, dzx. dxx, dzx. Let's look up the table. xx, 0, zx, infinite. So 0 here, infinite here. Comparing the two, yeah, 60 better. Okay, therefore, shortest distance from y to x is now, yeah, the direct link xy. And then the next point in time in T1, z here is going to receive the distance vector from x and y, and this time dyx is 60. That's going to change, yeah, the result of the dzx, this entry here. So let's see, dzx. From z to x through two neighbors, link cost being 50 and 1. 50 and 1. dxx and dyx. dxx, dyx. So xx value 0, yx value 60. So 0 here, 60 here. So comparing 50 to 61, 50 wings. And you see here, from z to x, yeah, we're taking just this link, zx, as a direct path to destination x. Quite different, isn't it? So we update dz, and dz is going to go to the neighboring nodes. Okay, and so y here, recalculating dy again, the dyx is going to be different as well. Okay, so dyx. Okay, two neighboring nodes, 60 and 1 are the link cost. dxx 0, dzx, zx, entry value being 50. So 51 compared to 60, 51 wings. So to go from y to x, now the shortest distance is, yeah, this path. And in fact, at this point in time, so let's update the distance vector for y. At this point in time, the network converge to the true shortest path. And it takes only what? 2 iterations, as opposed to 44 previously.
Okay. Well, that is not exactly correct. At that point, it's not quite yet converged because at T2 there, because table on node Y gets changed. So it will be propagated one more time, but there's not going to be any more change later on. Okay. All right, so that finally concludes distance vector. The original way of calculating it seemingly straightforward. If we do it on a new network, no problem. If there's a good news, no problem. But if there's bad news, then you see situation gets a little bit complex. Because the way computer memorizing things and using the old information to try to update routes, okay, and that old memory gets kept somehow, okay, in this local exchange. Now, let's summarize link state and distance vector.
Now with both routing algorithms introduced, let's compare the two algorithms. LS here stands for link state. DV is the distance vector. Let's compare the message complexity first. If you recall in link state, each router there needs to generate this link state report, and it gets propagated, broadcasted throughout the network. So each of these link state reports is going to travel all the links, and there are E of them. And there are n nodes, each will be generating these link state reports. Therefore, overall cost and in the worst case, in case the network is very good, very well connected, yeah, the E here is about the scale of n squared. Okay, so overall, the cost can go as high as n cubed. So link state message complexity, not good at all. Distance vector, on the other hand, okay, the message exchanges between the local neighbors. Right? And as you see in one of the examples earlier, as soon as the route converges to the shortest, no more distance vector messages being passed further. So there seems to be some opportunities for some node to stop message passing early. Yeah, so in terms of message complexity, DV is slightly better. Now, the second metric, speed of convergence, the time it takes to converge to the shortest path. In link state, it runs the Dijkstra algorithm, which we know the time complexity being n squared. There's some optimizations one can apply that takes you to n log n time, even better. So link state seems to be okay, except that we need to be careful about setting the link cost. Try not to use the traffic going on the link right now and changing it dynamically. On the other hand, in distance vector, well, the convergence time varies. In some of the earlier examples we see, in a 2-hop network, it takes only 2 cycles to converge. So if you think about it, the convergence time for a network is pretty much, okay, in the scale of the diameter of the network. But that is actually in the ideal situation. Okay? What if we have bad news that we need to propagate through the network? Then we could run into the count to infinity problem. And during the phase of counting to infinity, packets will be looping, okay, from router to router. So in distance vector, yeah, the convergence time is a little bit hard to predict. It really depends on the situation. Okay? On the other hand, link state, very predictable. Okay? I would say in terms of predictability, link state wins, okay, over distance vector. But under normal situation, distance vector's convergence time, yeah, it's indeed the diameter of the network. There's not many hops, okay? Even for a large network, okay, the diameter might not be so long either. The third matrix to compare, the robustness. What if a router is malfunctioning and reporting the wrong link costs? Okay, things like that. In link state routing, during the phase the router is malfunctioning, yes, okay, the neighboring nodes will be advertising the wrong link state reports. Okay, and each router will be calculating the shortest distance based on the wrong link state report. But once, okay, the malfunctioning goes away, link state report will be corrected, and quickly each router will be calculating the shortest path based on the correct link state report. So the time you expect the network to recover from the router malfunctioning is expectable in link state. In distance vector, however, okay, if a router is malfunctioning and reporting, for example, a short cost, okay, short link cost to a particular neighbor, okay, yeah, the node can actually falsely reporting the shortest path to a particular destination being shorter than expected. So these incorrect paths gets advertised and propagated out. And the neighbors of these nodes is going to take it and potentially include that in the shortest path and updating the DV and then pass the incorrect information further. Yeah, each node's table is going to be used by the other. Each node's distance vector is going to be used by others. This error is going to propagate out throughout the network, and it might take a long time, yeah, for the network to recover to the correct cost. Taking a long time and not very predictable. So in terms of robustness, yeah, link state here is still, okay, winning by a head, by a neck.
All right, good. So you see, link state, distance vector. Although we try to go with link state, although we try to go with distance vector because link state does have this high memory cost, right? But we also see distance vector is not like the savior, okay, of the world. You could have this count to infinity problem, and all information might get propagated out, and it takes a long time to correct. And it's hard to predict exactly how long it's gonna converge. Now, so trade-off, essentially. Okay. Now, we only have like 18 minutes left. This is not gonna be enough time to actually cover even section 5.3. So what I would suggest is we do this. Let me go over the exam 4, the things that you want to be pay attention to first. So this is the exam 4 channel. It's gonna happen on Thursday because all of you will be taking the exam online. So you'll be joining a Google Meet session. Okay? And there are so many of you. We're gonna need to check the IDs because I'm not quite sure if I recognize all of you. Okay? So Caleb and I will somehow distribute the work and manage to do the checking. But we do need some time to do the ID check. So all you need to do is just to show your ID with photos in front of the camera so we see the face and the ID's picture. So this might take some 15 minutes time. If you are able to come earlier, that's great. I think at least Polly will be there online since starting from 1 p.m. from 13:00. Okay, and we'll try to start the exam punctual at 1:20, and it will run until 2:10 p.m. And I just changed the exam scope given the progress of the lecture. We will cover the entire chapter 4. We'll cover 5.1, which is only the overview of control, and it's more like a review of network layer and then the control plane. 5.2, link state and distance vector routing. The Google Meet session will be here, and the Google form for the exam will be here. Now, I know that many of you have not yet done the exams remotely, so you will need to try using Google Meet, maybe with your friends, okay, where the camera is proven working, and your camera should be like taking your facial or upper body shot, so that essentially we see you, okay, and we need to see you throughout the time of the exam. Okay, so make sure your camera is working and your head and face would appear, okay, in the camera view the whole time, okay, within these 50, maybe 60 minutes. So that's all for exam 4. Once again, as you see, when you guys are working on the quizzes, hey, whether you get it right or wrong, it's not the major point. If you get it wrong, then it's an opportunity for you to reflect. Okay, similarly, right, you see Polly getting things wrong also, iterating things or thinking about it after a while. So what I'm trying to say is that we can get things wrong easy. Okay, so quizzes being there and exams being there are there for you as an opportunity to reflect in case you did not get things right during the lecture. And the rest of the time, we have 15 minutes left. So what I would suggest we do is to try to go through this example here so that we show, for this case, X and Y and Z, which is connected this way. 4, 1, and that's all. There's no link between X and Z. And see if we need to count to infinity. Okay, how about that? Okay, shall we go with it? Okay, so let's change the link cost from 4 to 60. Okay. And before that, the base table should be somewhere that's XYZ with link cost 4 and 1. Okay, and it's already converged. Now, as human beings, we know, right? In case, okay, let me go back. Okay, I can't because then I have to redraw everything. So if this link cost is 4, this link cost is 1. What is the shortest path from x to y to z? Well, x to y is 4, x to z is 5. So, hey, the original table actually still holds. Okay, why? This link here would cost 50. Chances, there's no chance that XYZ would try to propagate data through this link. So this topology here versus this topology, the routes are actually going to be the same. Okay, so the original table are actually the same. Very good. Now, let's change link cost from 4 to 60 here. To calculate these, what do you think? Oh, okay, it's a little bit tricky. We don't know, right? Because 51 and 50 obviously are the result of having the link cost being 50 here. So why don't we calculate this ourselves and once? So dxy, okay, will be between x to first neighbor and then from the neighbor to the destination. Now, how many neighbors x has? There's only one this time, right? Because there's no link between x and z. So obviously, just y here and y here. Sorry, I need to add these two. xy is now 60 and this is 0. 60. So this is going to be 60. What about dz? Let's calculate. C x to the neighbor plus neighbor to z. Well, x has only one neighbor once again, so this is still 60 plus 0. Oh, yeah, so wait. Oh, wait, no, not quite right. Y to z, oh, sorry, this is 1, so 61. Okay, very good. So this should end up being 60 and this should end up being 61 in this case. Now, what about these? If we have this topology, well, calculate dy to x. So this is coming from y and going to x as the destination. Now yo has two neighbors, so x, and we need to compare to another entry, isn't it? Z. What is the value here? Yx is changed to 60, dxx 0, so we do have 60 here. What about this guy here? cyz is 1. And the zx is 5. We have 6 here. 6, wait. Yeah, 60 and 6 here. Alright, so to go from y to z, wait a minute. To go from y to z, You see, Polly got stuck here. Am I right? Yeah, I think I'm right. Right? It's just weird. You see? Yeah, it's just weird. Okay, so 60 and 6. So let me write it down. 61, 60 here, 61 here, and then 60 here and 6 here. Oh, YZ is not calculated. Yeah, you're right. So 6 still here. Okay. But DYZ, thank you, Sue. It should be DZ. Yeah, it should be 0. Okay, so let's do it again. Thank you, guys. Yeah, take mean of these two values. Exactly. Okay, that's where I got stuck. So let's do it again. How about that? Yeah. Yeah, you see, Polly gets stuck. So tricky, isn't it? Let's do it again. DYX. Yeah, this is the goal. So we need to do Y plus D to X. First neighbor, X, X. Second neighbor, Z, Z. So this is 60 and this is 6 and we take the minimum. All right. Haven't calculated Z. There we go. Thank you. Now from Y to Z. Okay. Z. So first neighbor, X. Second neighbor, Z. Yeah, this is 1. And this is 60 plus X to Z 0, X to Z 5. So 65. And we go with the smaller value. There we go. Okay, so this is fine. 601. And I think this is 60 and 61, if I recall correctly. Okay. So 60, 61. And this is still 601, right? So calculating, need to get the topology out again. It's now 60 and 1. ZX will be this plus this and another neighbor, but Z has only one neighbor, so we don't do this anymore. Just Z through Y. ZY is 1. The YZ is 1. This is going to X. So YX 6. Yeah, still 6. So still get 7. Similarly, to calculate DZY, we try only one neighbor. ZY is 1. DYY by default 0. This is 1. Okay, so this 7, 1. What about this? Even if this is 60 and 61. Well, DYX, it's the minimum of these two. So dy has two neighbors. We still need to calculate them both in order to do the Poisson reverse. Okay, so, okay, Ziyao, I will come back to your question. So CYX 60 plus 0. CYZ is 1. And ZX is 7. So 8. So this entry is still 8. And we can probably skip calculating this because 1 is hard to beat, isn't it? And this A01 will come to know Z. And it will grow and grow and grow until when? And it never ends. Yeah. So, indeed, with this case, it will count to infinity. Because there's no other route except to go to Y. But Z is always under the perception that there's a better way. No, wait. I think Y might actually take... Is it? Ah, okay. Interesting. Yeah. Good. Yeah, Evan, you are thinking what I'm thinking, indeed. Because Y here, as it's calculating its route to X to Z. So, in the end, this entry, this is gonna grow bigger than 60 or reach 60 because 7, 8, 9, 10, 11, 12. Eventually, this will get to 60 and this is gonna be bigger than this. And therefore, when that happens, we stop at 60 because all the subsequent longer routes here will not be bigger than 60. Yeah, so we will converge even though it's called count to infinity. Yeah. But maybe there'll be some case that we do need to count to infinity. I think it might be, right? Because if this one breaks in this topology and we break this link, yeah, I think then we get count to infinity. Alright, so I think we played around enough, okay, brainstorm around enough about the count to infinity problem. Now let me come back to Ziya's question here. In order to do the Poisson reverse, the router not only record the minimum distance to other routers, but also has to record those routers on the way. Yes. So there needs to be additional message exchange between the router that detect a broken link or a worse link to all its neighbors. And in fact, what happened is this, okay, Ziya, if you look at this table, I see. Because the distance vector here does not... Give me a second. Yeah. So what I'm showing here in the distance table here are just distance. In fact, okay, there's something else in the distance vector that the routers actually keep. For example, x to y, the minimum cost is 4, but it also keeps x to y, the original topology, the next hop being y. From x to z, the cost is 5, and the next hop from x to reach z is y. Okay, so this information is actually kept in dx as well. Okay, but in the calculation, we don't really need that. But in case of doing Poisson reverse, yes. For example, y and x here, once detecting this link is getting worse or broken, it's gonna probe all its neighbor, okay, and Z here is gonna send its DZ again with the next hops. And if Z sees there in any of the entries in DZ, the next hop is Y, then Y will send a message back, hey Z, you remove that entry and set it to infinite. In the meantime, Z here will set that entry already in the table to infinite. Okay. Exactly. Very good question there. All right. Oh, by the way, the time is already up. So Polly was wrong again that with this topology, it doesn't quite count to infinity, and this topology. But if we break this link entirely, not reducing it from 4 to 60, but from 4 to infinite, then I think we do have a count to infinity case. But hey, don't take my words for it. Guys, think about it. Maybe it doesn't. Let me think. No, this time I think it's really counting to infinity. Okay, let me know in case I'm wrong. Okay, good. And so that's all for the lecturing. The last time we meet will be Thursday. Okay. Good luck. And not just for this particular exam, but also the rest of the semester. Yeah, so this is what I was hoping we can cover at least for this week. Alright, so let me end the stream here. Okay, ciao.